So this summer I spent a month at Harvard. I worked with Jerome and Haitong, mostly under Professor Shang's guidance, and working on an ultrasound arm here. There we go. So our goals was to use the UR5E robot arm to be able to automatically perform an ultrasound scan using image planning with the RealSense camera. So we plan our path using the camera by finding the vital organs, and we reach that target organ autonomously through our path planning. So the way we went about that is we have our UR5E arm here. Then we attach an RGBD Intel RealSense camera on top, and then we also add a ultrasound probe all on the end of the bot here. So the purpose is to because of the cost for follow-up patients is expensive, and we want to be able to automate diagnosis and be able to scan for the liver and cardiac diseases in between the CT scans. And here's a picture of us of the robot arm scanning on an imaging phantom, which is basically we don't want to be able to test it on a human because if it goes wrong, if it pushes too far, if it goes like hit something, someone's hurt. So if there's errors, this is good and it's accurate with the human abdomen. There we go. Okay, so in our first week or first days, Jerome had some 3D printed parts, and so what we used these for was to, on the right here, as you see, we attached the RealSense camera to the end, so we were able to communicate with the camera, and then after it sees the target, it can communicate to the arm to where we're supposed to move. And here's the attachments and the ultimate design here, where we're supposed to have the ultrasound probe here, and then the camera up here. So the RealSense D405 is the camera we used here. It has a depth perception camera and a RGB camera. We didn't really use the RGB one, but the depth perception is really useful because it can be able to have depth perception, and you can see in 3D models. So therefore, we use Aruco marker detection. So we have our starting point, which is 000, the origin, which is the camera, and then we have the Aruco marker, which we move towards. So the RealSense is used for this. So Aruco markers are binary square fiducial markers. So what that means is they're binary and square. So square means 2 by 2, 3 by 3, 4 by 4, 5 by 5, and so on. For these, I believe we use 6 by 6, and then the binary part means it's either black or white, and then that gives it a unique ID. And then they're fiducial markers, which means like similar to like how shears or whatever work in linear algebra and like how 3D games are programmed. We can immediately tell how far away an Aruco marker is, where it is its coordinates compared to the camera itself, which means we have our starting point and our end point and the coordinates for those, so we can know where to go. And yeah, and the markers give the exact size or whatever and the exact distance, which is really helpful. And then to control the arm and connect the camera, we use ROS, which is a robotic OS. It's meant to be universal and applicable on any robot for any code. So, and it sets a standard for pretty much all coding of robots. So programmers don't need to waste so much time on reinventing the wheel and creating new software for each and every robot. So mainly we use the nodes and topics, which are the code and the commands we send to the robot to execute, and topics, which are the communication process. And yeah, as you see here, we have our program A, and we use the ROS communication tools, and mostly topics, and we communicate with the program B, so like nodes to topic to node with the publication to subscription type. So here's the flow chart. Oh, my bad. Here's the flow chart that will work for this project. So we have a RealSense camera, and it gives us the input, which is the Aruco marker. We have our starting point and our end point, and we can create our two other control points using these two. So we have a RealSense camera. We use, and it's connected with the USB to the laptop. And we use the laptop's ROS to be able to give commands and have the code that uses the input we have for an output, which is the ARM response. However, we encountered issues with the ROS versions because the Ubuntu 22.04 was the only one that supported RealSense, and we had 20.04 and ROS 1 on the laptop. But however, Yeah, see, ROS1 didn't support RealSense and ROS2 didn't support MoveIt, which is connected to the virtual environment, and the connection needed to actually control the arm. So we used a virtual machine here to be able to connect ROS1 and ROS2, so we could have you connect both the camera and the robot arm with two different versions of ROS here. So yeah, here's some code from the thing. So we use ROS and ROS2 simultaneously, as aforementioned, to control the arm. We have the ROS for the robotic arm and the ROS2 for the camera, and then we use a laptop as a central node to connect the two. So we see here we have our ROS2, so we launch our driver and our Python code, and we have our UR type, our robotic arm type is UR5E, and we have the IP address because we're connected by an Ethernet cable. Now we use fake hardware and launch the virtual environment. And as you see here, this is a virtual machine. So as you see here, this is a 20.04. On the actual laptop, we have 22.04, so we can support the camera. But we need to go back to 20.04 and ROS1 to be able to connect with both the robotic arms virtual environment and the new 22.04 and ROS2 with the camera. Okay, so the virtual environment we used was a Gazebo and RViz. So here it's a virtual 3D visualization tool for ROS. And so what it does is it uses a URDF file of a robot model to simulate the real version. And what the URDF is basically a description of all the joints and parts of a robotic model. For example, here, for example, we say this thing is a cylinder, it's this long, it has this density, has this mass, it follows normal physics. And we do that for every joint and motor and part for the arm, and that gives us our file. And based on that, we were able to move manually with this environment. Oh, there we go. It's the video is loading. But yeah, so through the RViz environment, we can manually control it. As you see here, we drag it to its starting point, from a starting point to an endpoint, and then it automatically moves, uses its own guided path planning. As you see here. So yes. There. Okay. Yeah, but unfortunately, we don't, with the RViz thing, we didn't really control the path planning itself. So it resulted in issues like this where, for example, in this first video right here, it didn't account for the camera on the end of the arm. So when it has its automatic path movement to go to its endpoint, it breaks off the camera because it's in the way. See, so yeah. And then here, yeah. So yeah. It's like, yeah, inefficient and like unwanted extra movement that wasn't what we really wanted. So yeah. And then as we see here, it bumps into the C again. But yeah, so that's it. So to fix this, we made our own path planning using a Bezier curve. So what a Bezier curve is, we use the cubic form, which is we have 4 control points here. As you see in the illustration, as we move from T from 0 to 1, it uses these control points to be able to create a smooth path straight towards the target. And then here's the formula. I see it's similar to a parametric equation or in terms of the T. So as we increase T and these change, and we use the P and repeat it for each like XYZ coordinate and include the rotation matrices in the code. So yes, here's the code I made for the Bezier function in the actual Python. Here is the definition of the Bezier function. These two just represent in code form the formula that I just showed on the last slide. This is the code here. So the input here is the 3D points of the 4 control points and the rotation matrices for each control point. So we have all 4 of our control points as their coordinates, and we set our divisions to 50, which means we increment t by divisions of 0.02. So from 0 to 0.02, 0.04, which gives us 50 points on our path to the target. So yeah, and yeah, see, and then so this is just the Bezier function, and down here, so like as you see here, up here, if found. So once we find our Aruka marker, we have our starting point, which is just our origin, which is our camera, and then we have our coordinates of the Aruka marker, which is our endpoint. We're able to run our code here, and then as you see here, so here are the camera nodes, which are our 4 control points. So we have our first one, and our second one is the distance divided by 3, and then the second one is 2/3 of the distance, or the endpoint, minus a third of the distance, whatever. And then we have our 4 control points, and then we are able to build our path using these 4 points. And then that results in our things here. As you see here, we have our P0, which is start, and P3 our end. As you see, our first control point, like they're connected here in Australia, and then here, which gives us like their normals are in a straight line, which means it starts here and then it curves up back to here, from P0 to P1 and P2 to P3. And then this is the path planning that's actually created in the RViz environment earlier, and with our 50 divisions here, which forms a smooth path to the target. And then, yeah, here's the formula for P1 and P2, which are control points, each a third at 0, 1/3, 2/3, and at 1. So here we're connecting to the UR5E using this. For example, here is our Bezier curve visualized on the imaging phantom. So you see it has all its divisions. It sees the Aruka marker, and it moves in a smooth curve straight to the target. There we go. So after we were able to achieve this, we had successful path planning. This is just our first test, or whatever, to make sure it actually went to the target. So this is just a piece of paper taped to a chair, so we make sure it works and goes straight on. Yeah.